The objective of my project is to use trajectory optimization to generate trajectories for quadrotors. Much of this project is based off the 2011 ICRA paper, Minimum Snap Trajectory Generation and Control for Quadrotors. The quadrotor dynamics are modeled using a 12 degrees of freedom state vector containing the position, orientation, and linear and angular velocities. Newtonian mechanics are used to model linear accelerations, and the angular acceleration model is shown here. This project leverages the fact that quadrotor dynamics are differentially flat with respect to the force and moment exerted by each motor. This means that if you give me a 4 times differentiable trajectory of position and a twice differentiable trajectory of yaw, I can tell you the necessary attitude and angular rates of the quadrotor body and even the necessary motor commands to achieve these states. This makes intuitive sense. If we know the necessary acceleration of a quadrotor, then we can determine the orientation of the quadrotor since it is only capable of producing thrust in the upward direction with respect to its body. The input to the trajectory problem is a series of positions and headings paired together as keyframes that are constrained to be the start of a trajectory over a time segment. An additional constraint is added to ensure that each derivative at the end of a time segment is equal to the derivative at the beginning of the next. To represent this, the optimization problem is formulated as a series of elements each representing a position and heading derivative at the start of a time segment. The quadrotor equations of differential flatness show the moments about the x and y body axes are functions of the fourth derivative of position, and the angular moment about the z body axis is a function of psi double dot. So trajectories are generated that minimize the magnitude of the fourth derivative of position and the second derivative of heading. In this way, the trajectory generation can be formulated as a quadratic program minimizing these values. A single-dimensional trajectory generated in this way is shown here. I was impressed by how easily this formulation fit into a Drake mathematical program and by how computationally inexpensive solving this quadratic program was. Additionally, impressive acrobatic trajectories can be found using this formulation. I show here a quadrotor passing through 4 keyframes in a vertical loop. I specify that the time between keyframes is small enough that the thrust vector must point down at the top of the loop, meaning the quadrotor must flip over completely to achieve thrust in the downward direction. Finally, I implement the controller described in the Mellinger and Kumar paper to track these trajectories in the presence of noisy dynamics. This controller uses similar concepts to those observed in the differential flatness demonstration. A desired force vector is computed as a function of the tracking error in position and linear velocity. A desired rotation can be expressed as the rotation needed to produce this thrust vector. Angular moments then follow as a function of rotation and angular rates. Put all together, the quadrotor can be given a series of x, y, z, and yaw keyframes, generate optimal trajectories to travel through these keyframes, and finally compute control inputs to track these optimal trajectories. I was impressed by how well the controller tracked many trajectories, however when velocities became too large, I found the gain matrices hard to tune to guarantee good performance.